Okay, this last part of lecture 21 beyond mass energy content of the universe. In particular, we'll talk about so-called dark matter. Uh, we'll talk about matter content, so it's useful to introduce a benchmark value, which is called the critical density. Critical density is defined to be 3 times the Hubble constant squared divided by 8 pi Newton's constant. And in fact, when we talk about matter energy density, we often take the ratio of that density to this critical density, and that ratio is denoted by capital omega. Okay, I would see such ratio determines the geometry of the universe. Okay. Of course, once you know the value of the Hubble constant now, you can find what's the critical density now, which rho c over 0. And the critical density now it turned out to be some 10 to the minus 29 gram per cc. Uh, it's an extremely small value. So it already corresponds to 1 nucleon per 200 liters. Okay, this is better than the best vacuum you can produce in a lab. Okay, so it's very, very small value of the density. And then we shall see, first we'll explain why this is useful benchmark. And besides that, also we see, turns out the observed density of the universe is very close to this critical density. So in other words, the observed omega is close to 1. Okay, and its implication for geometry, all this we will talk about. First, we're going to talk about so-called the baryonic matter. Uh, Regular matters are made of atoms, which in turn are composed nucleons, protons, neutrons, and electrons. Since nucleons are about 2,000 times more massive than electrons, so the mass of ordinary matter resides mostly in nucleons, which in particle physics classification are proton, neutron are baryons. Hence, ordinary matter in cosmology are referred to as baryonic matter. So when you hear baryonic matter, simply means ordinary atoms. Of course, some of the baryonic matter shines, and shining stars are composed of baryonic matter, and their cosmic density, we call the luminous density, can be deduced from observation by first you look in one area very carefully, and you can deduce the luminosity to mass ratio. It was given a certain mass, you expect this amount of luminosity. Okay, and then uh, if you think this ratio should hold for all of the universe, then by just looking just looking the survey the luminosity all over the universe, you can convert that into the mass density. So that's the mass density of the luminous matter, and the omega or the critical density turned out to be about a 0.5%. Okay, and of course, baryon matter also in the form of interstellar intergalactic gas that does not shine, but is subject to electromagnetic interactions that can thus be detected with absorptions. Uh, it turns out we have a method to use directly the total baryonic matter. It was not only the luminous but also the gas density and the total baryonic density, regardless whether it's luminous or non-luminous, because the light nuclear element, helium, deuterium, they are produced predominantly in the early universe at a cosmic time about 100 seconds after the Big Bang. The abundance, in particular deuterium, is very sensitive to this baryonic abundance. From such considerations, again, we will discuss later, you'll find that the total baryonic density, omega, is about 5%. So most baryonic matter is in the form of neutral interstellar and the intergalactic gas. Now we're going to talk about dark matter. there's compelling evidence that the vast majority of the matter in the universe do not have electromagnetic interactions. Hence, we cannot see it through emission absorption of the radiation. Its presence, how do we know then? But the presence can be deduced from the gravitational attraction. This dark matter is more than 5 times abundant as the baryonic matter, giving a total matter density of which is sum of the baryonic with dark matter. The baryonic we said about 5%, and turns out the dark matter is about 5 times, about 0.27, so give a total of 0.32. So omega is about a third. Now, the first person suggested there's such thing as dark matter as Fitzgerald in the 1930s. That's when he worked on the observed velocity of galaxies in something called coma cluster. Then he found the combined mass of all the visible stars and gas in the cluster simply is not enough to hold these galaxies together. So he suggests there must be some invisible matter, which now we call dark matter. Okay. And his theory was not picked up by other people, so it was sort of in the background, and I think most people forgot about it. And then other things slowly began to, and in particular, when people discovered this called this behavior, so-called galactic rotation curve in the late 1970s, then the whole dark matter idea revived and become taken much more seriously. If you consider, say, a galaxy, let's say spherical, it could be ellipsoidal, but anyway, spherical galaxy, and you talk about the effect of the gravitational attraction on a mass m. Okay, now assume spherical symmetry, so you can draw a Gaussian surface from the center of the distribution. So all the matter outside this Gaussian surface will not contribute to its attraction to this point m. Okay, only the interior mass will contribute, and you can from that you can work out that the tangent velocity by relating the centrifugal acceleration to the motions is by square root. It should be square root of the interior mass over r. Okay, so therefore you expect inside this gray area is the visible area, and outside will be for r small r greater than r. But anyway, for m inside this visible distribution, because then the big M should be proportional to the cube of the small r. So when r cancel, square root of r squared will be r. So therefore, you expected this curve to go linearly. Okay, but once it's outside the visible area, because now m is constant, so therefore you expect this to fall like 1 over square root of r. Okay, so you expect a distribution like this. Turns out the observed distribution is yes, does increase to the edge, and then it doesn't fall. Just go as far as you can see. This curve doesn't fall. So that's taken and suggested and taken by most people. That's evidence of dark matter. And there are many other this type of argument for the existence of dark matter due to that gravitational attraction. And a general picture emerged is that you have a distant star. Here is on side view of a galaxy, and which stars and the galaxies in a large, but then it's surrounded by a big halo. Okay, the halo is mostly dark matter. Okay, so of course this is an idealized picture that you have a disk of baryonic matter embedded in a halo of dark matter. Okay, now of course here idealized in the sense it's dark matter is like a sphere distribution, but actually in reality dark matter may not be spherical and its distribution not be smooth. In fact, there are theoretical and observation ground to expect the dark matter spread out like an inhomogeneous web, and the visible stars are usually congregated at this dark matter potential wells at places that are more dark matter, and there where the visible stars fall into. And this picture, dark matter halo, dark matter webs, is a computer simulation uh, of dark matter distributions. So the question, what are these dark matter? What make up the dark matter? Okay. First of all, we classically call cold and hot dark matter. For example, neutrino, which have only weak interaction, have no electromagnetic interaction, is an example of dark matter. In fact, we call neutrinos an example of hot dark matter because being extremely low mass, almost no mass, they typically, you give it any kinetic energy, it goes move as close to the speed of light, relative velocity. Okay. But the study of galactic structure formations have concluded that most dark matter are in the form of cold dark matter, which means they are heavy and non-relative particles, not like neutrinos. So neutrino cannot be the dominant dominant dark matter. But there are no known particle fits this cold dark matter description. It's commonly held there are undiscovered elementary particles beyond those known in the standard model that can be hundreds, thousands of times more massive than nucleons. These we call weakly interacting mass particles, the WIMPs, may form the cold dark matter. Okay. And the theory's favorite WIMP candidates are so-called the lightest supersymmetric particles. But in fact, right now, the highest accelerator experiments, we still have not seen any supersymmetric particle. Doesn't mean the supersymmetric theory is dead. Simply means it's not as simple as we thought, if they exist at all. In short, cosmic matter have two components: the familiar baryonic matter and the dark matter. Dark matter may some unknown collisionless particles. Collisionless because they interact so weakly, so they don't collide. They go through each other. So because they have no electromagnetic interactions. Here is something called bullet clusters that's taken by many as to be direct empirical evidence for the existence of the matter made two components, baryonic plus uh, collisionless dark matter. Here are three images of a galaxy, a particular galaxy, and now nicknamed the bullet cluster. The first picture is on the left-hand side is a Hubble space telegram picture of, the usual picture you see, composed of showing all the galaxies, make a few percent of the cluster mass. And then on the right-hand side picture is the X-ray image of the same area by the Chandra telescope, X-ray telescope, showing the bulk of the hot gas is located. See these? Okay. And so these two images, and superimposed on both images, or the third images, are superimposed are the mass distribution deduced from gravitational lensing. Remember, light bent by the mass, and from this we can deduce what the masses are. And these contours show the two mass peaks here, okay, and more or less tracks the location of the observed galaxies, but far from away from the atomic gas. So the interpretation is that the observation shows that the bullet cluster a result from a collision of two clusters of galaxies. The dark matter and baryonic matter are separated because the weak dark matter pass through like a bullet. Okay, they go through each other because they don't interact, they don't collide, leaving the uh, uh, but the baryonic of course collide, get heat up, and especially the gases. So the galaxy remains trapped in the ordinary galaxy are trapped in the dark matter potential wells, but the gases are heat up and the radiates. So that's the evidence for direct evidence for dark matter. So here are the takeaways of lecture 21. Uh, General relativity provides a natural framework for study cosmology. And Lamartine and the Hubble each discovered independently that the universe is expanding. Everything was concentrated in the tiny region of extremely high density. Everything was. So the observation, that's the Big Bang, and the observation estimate age is about 12 to 15 gigayears, a billion years. The mass density of the non-relative matter in units of critical density is about 0.32, made of baryonic matter, which is ordinary atoms, which is about only 5%, plus the non-luminous, non-baryonic components having no electromagnetic interaction. These are dark matter, which is about 0.27. Only a tenth of baryonic matter uh, luminous, and the luminous density, the ratio omega is about 0.5%. The rest are interstellar and intergalactic gases. Next lecture, we're going to talk about setting up the GR framework for a homogeneous isotropic universe, and the geometry turned out to be described something called Robertson-Walker metric. And this basically was setting up the kinematics for GR study of cosmology. And the lecture 23, following that, will be studying the dynamics of such a cosmic model. Okay, so that's it.